Hello, I'm Evan. Quantum mechanics has sort of become synonymous with difficult scientific mumbo-jumbo. And although the math might be a little difficult to understand, the theory itself really isn't that hard to grasp. Ever wonder what it's all about? That's the name of the show. Ever wonder? Physics has traditionally been about understanding the really big things, like planets and stars and galaxies and the universe, and really small things, like particles and waves. In the 19th century, physicists were getting a little bit cocky. A physicist by the name of Lord Kelvin supposedly suggested that there was nothing new to know in the universe. In some, it seemed as though what was once a beautiful, immaculate, and mysterious universe was becoming predictable, an empirical beast. It was as if soon there would be no more mystery to our own physical reality. However, the universe is a fickle mistress. There were already hints that something was amiss as early as 1803. A physicist by the name of Thomas Young was conducting experiments with light particles and realized something very strange. Light, and particles in general for that matter, were always thought to behave exactly like little billiard balls. You could hit them around and they'd bounce and they'd make atoms and molecules and all sorts of crazy stuff, but they would always be wonderfully predictable. What I mean by that is if you had a calculator, a really good eye for counting, a supercomputer, and a lot of free time on your hands, you could sit down, look at what every particle is doing, where it's going, and use that to infer where the universe as a whole is going. Essentially, you could predict the future. Because of this, there was a philosophical movement called determinism that asserted this wouldn't only apply to the physical world we live in, but also the mental one. Emotions, feelings, thoughts, all of it, everything that made us human, could be predicted through particles and physics. Getting back to Mr. Young and his experiments with light, he noticed something very bizarre. He was shooting light particles through two slits. Now, if light particles were billiard balls, what we would expect is that after going through the splits, there would be two strips of light that would go through, hit the wall, and we'd have two strips of light on the wall. Makes sense? What he was seeing was something very different and bizarre. He was seeing wave patterns on the wall. Some parts of the wall were brighter than others, other parts were dimmer than others, but it wasn't the two nice, friendly slits we expected. It was as though the particles were interacting with each other and causing ripples that made high points on the wall and low points on the wall. There was even more evidence coming in that something wasn't right. In 1905, Einstein conducted an experiment called the photoelectric effect. What he concluded was something even more bizarre. Not only does light behave somewhat like a particle and somewhat like a wave, but it's only allowed to take certain energy levels or certain quanta of energy. Because of this, you have a very, very strange situation. It was the first instance where something in the universe was not continuous. It was as if you're trying to fill a glass with milk, but you were only allowed to fill it to certain heights, not any height you wanted. This was insane. The physics community was very worried. Things got even worse in 1927. Heisenberg studied an effect he termed the uncertainty principle. It effectively stated that you can't know everything about a particle. The more you know about where it is, the less you know about how it's moving, and vice versa. The more precisely you know one feature of it, the less precisely you know the other. Because of this, it was realized that we needed an overhaul of physics. It was realized that the universe worked in very strange and mysterious ways. And I want to emphasize that this was not a measurement error. This is something fundamental, something intrinsic to the way the universe works. Remember the theory of determinism? Quantum mechanics killed it. How can you predict the future if you can't even predict the present? In the year 1930, Max Born said, "Physics as we know it will be over in 6 months." And he wasn't too far off. It was clear that we really needed to reevaluate a lot of the assessments and a lot of the assumptions we'd made about our physical world. Einstein said in 1950, famously, "God does not play dice with the world." And now we know that he wasn't quite right, but at the time, it was very hard to accept these new realities. It was clear that no longer can we take particles to be little billiard balls. There's something much more complicated. So what do we know today? When we consider particles, we no longer take them to be little rigid balls moving around with predictable motion. Now we consider them to be waves of probability. A particle is probably here, but it could also be here, or here, or here, or way out there. And once again, this doesn't have to do with measurement error. The particles actually spread out over a wave of probabilities. In addition to this, the universe gets lazy when it's considering particles. When no one's around, it keeps a rough estimate on where everything probably is. So how does this affect the math in quantum mechanics? Well, instead of using classical assumptions, we use something called a wave function. It's a cool little term that's using the Greek letter psi, and it tells you not where the particle is, but where the particle probably is as a function of time. When you look at a particle, its wave function collapses to a point, and suddenly the particle looks like it's behaving like a classical little billiard ball. But as soon as you look away, it goes back to being a wave of probabilities. Because of this, we're able to explain interesting phenomena that we weren't able to explain otherwise. One of those is called quantum tunneling. This is really cool. If you have a wall, or a potential well as we call it in physics, and a particle comes up to it, classically, you can't go through a wall. But in quantum mechanics, because you're a wave of probabilities, there's a probability you're on the other side of the wall. So if you look away and look back, the particle can somehow make it to the other side of the wall, something that quantum mechanics was finally able to explain. Another assumption is that you can actually have particles come out of seemingly nowhere. This sounds bizarre, and it would be if it weren't for Einstein's great equation that everyone knows because it's the most famous equation, E equals mc squared, which tells us there's a relationship between E, energy, and m, mass. What can happen is a light particle is traveling along, energy, and you're not looking, quantum mechanics decides to pull something, and suddenly you have two particles come into existence effectively. Although keep in mind they were born of the light. These particles, though, are oppositely charged, so as soon as they've come into existence, they get pulled back together and turn back into light. This is being observed. We know it happens. This means that space, an infinite, huge, giant realm of nothingness, actually is full of a huge amount of action, which constitutes these particles bursting into existence and then quickly canceling each other out and turning back into energy. Kind of cool. Quantum mechanics is a driving force between MRI machines, electron microscopes, microchips, and even plays a part in getting a light switch to turn on. There's also been a huge push lately to develop a quantum computer. It sounds sci-fi and kind of cool, but it's not that hard to understand. Computers traditionally operate on a bit system in which data is stored either as a 0 or a 1. Because quantum allows you a bit of ambiguity as to what something actually is, you can store data in a superposition of 0 and 1, something called a qubit. Qubits have already been developed, and because of this, it's realistic to say we might see quantum computers within our lifetime. They're going to be hugely more powerful and fast, so yay quantum! Quantum mechanics seems scary and arbitrary at first. No one in the scientific community expected it, and we were all horrified by the discovery. But the more you work with it, the more you appreciate its beauty. It paints a much softer picture of the universe, in which matter isn't held to these discrete points in space, but spreads out to embrace whole sections. It tells us that the universe is mischievously playful, yet ultimately efficient, so long as no one is looking. But most importantly, it gives an example of the truest incarnation of science, in which we didn't want this story to be true, but experiment after experiment told us it was, and because of that, we need to accept it, because physics does not lie.